In this video, we will solve this or model this rotational mechanical system. Okay, so in the system we have two inertias, as you can see, JR and JL. Okay, these are two independent bodies, and they are connected through a torsional spring, which has a stiffness of kappa or K. It doesn't matter. Both of the dampers are technically affected or technically resisted by viscous friction. First one has a viscous friction coefficient of dr. Second one is viscous friction coefficient of dl. Okay, and these frictions are only affecting the body it's acting on. The dr is not affecting jl, dl is not affecting jr. Input of the system is this external torque. Okay, so this body or inertia has an angular velocity of omega r. The second body has an angular velocity of omega l. Okay, so we have angles theta r and theta l, and they are technically measured with respect to its initial position, and we assume that the stiffness is at rest in the initial conditions. Okay, so the body is in technically steady state motion. Okay, so in this problem, I also uploaded the example PDF and solution. You can look at that. It is given that the state space is omega L. Omega L is also output of the system. Okay, it's given. Is it omega L? Yes, it's true. Omega R, the angular velocity of the second tank, and the third state is equal to theta R minus theta L. Okay, so this is a valid state definition for the system, and from this perspective we know that this is a third order system. Okay, so what we can do is, if I don't give you this state definition, you may assume that or guess that your states are omega L, omega R, theta L. Okay, so that it is fine. It's not exactly true, but it's not exactly wrong. And as you can see, this is a fourth order system, but it's a third order system. Okay, since my output is angular velocity here, I really don't need to assume that my theta r and theta l are as separate states, which is technically wrong, but I will talk about this later. Okay, so if you remember previously, I told you that the main variables, okay, the core variables in rotational mechanical systems are the velocities or angular velocities and forces. Okay, so angular velocity and forces, but the position is not technically a main core state variable. We really use force only if we want an output that is in terms of force. If I want you to have output of theta L at your output instead of omega L, the speed, then you may need to use the other definition. Okay, omega L, omega R, theta L, or something like that. But my output is angular velocity. I may use position. I'm still using position, but it is different. I'm not using these positions or the angles of these bodies independently. As you can see, I'm just using the difference. Okay, so when I tell you that the main core variables, especially state variables, are angular speed and force. Of course, I'm using angular speeds, as you can see here. But what is theta r minus theta L? Okay, this is a torsional stiffness. And what is the torque of this stiffness acting on this body? If I assume that theta r is larger than theta L, technically torque, or let's say torque, it's better, is equal to kappa times theta r minus theta L. Okay, so when assuming my state as the difference between angles, I'm technically also assuming that my state is an linear, or let's say proportional to the torque of the torsional spring. So I'm technically using torque as my main state variable, or at least something very close to that. Okay, so from this perspective, the take-home message is, if the state definition is not directly given to you, you should be a little bit careful. Okay, one way of understanding how to choose state variables or order of the system is drawing the circuit equivalent of the system. Okay, so this is as you can see, a capacitor. We know that. Okay, we have a capacitor. The inertia is always capacitor. Capacitors are connected by an inductor, another capacitor here. Okay, that's great. And we have technically a current source, which is torque here. So I have two capacitors and one inductor, and if I use technically the inductor's current, if I don't use any variable that's not directly inside the circuit, okay, so, then this is a third order system. Like if I want to use some other variable, okay, so for example theta L, which is the integral of the capacitor, obviously it can increase the order, because integration of a variable can potentially increase the order of your system if this integral is not directly embedded in your electrical circuit or mechanical circuit. Okay, so these are some details I want to talk about in this video, but from the perspective of solving this problem, the state definition is given to you, so I made your life easier. So what are we going to do is write equations of motion and then try to find the full state space representation. Let's start with the first one. Okay, so let's write an equations of motion for the first disk, right, or first body. So we know that JR times omega R dot, okay, that's true, is equal to total torque acting on this body. As you can see, this torque is in the same direction with the angular velocity, so it is affecting like this, okay. So damping always resists the velocity. It's in the opposite direction. Okay, so dr, okay, times omega r, okay. Then we have a stiffness force. Okay, so if you remember, we need to have some sort of convention if a stiffness or damper is connected between these two different variables. When it's connected to ground, which is easy, but when it's connected between two variables, it can be a little bit tricky. Okay, so I assume that this torsional stiffness applying a torque in this direction, so as technically resisting the motion of the system, so it should be negative. Okay, so if this is the case, I technically know that theta r, okay, the technical angular displacement of the first disk should be larger than the angular displacement of the second disk. Only in that case it can resist the motion in this direction. So kappa times theta r minus theta L. Okay, that's good. So one way of checking if it's correct or not is that, so since we are writing an equation of motion with respect to axis r, okay, so in this equality, in this part, as you can see, this is minus because theta r is here. If I write theta L minus theta r, it will be wrong. It will be some sort of an active component, but we know that it's a passive component. Okay, so what I'm going to do is, instead of technically moving at the equations, I will simplify this equation using my state definition. Okay, so omega r is my second state. So JR times x2 dot. Torque is my input, which is equal to U. dr omega r is my second state, minus kappa theta r minus theta L is my third state, x3. Okay, I think that's great, right? So I will further simplify it such that, so let's write it here. I will use it later. I can simplify this state equation like this. Is equal to 1 over JR times U minus dr divided by JR times x of 2 minus kappa or k divided by JR times x3. Okay, so we computed one of our state equations here. That's great. So let's change the color. Okay, and let's clean that and move on with the second disk. Okay, that's super great. Which is slightly easier. Okay, so we have a disk. This is affected by a viscous damper, and this torsional stiffness also driving this disk. Okay, this torsional stiffness is resisting the motion of the first disk, but it's technically driving the second disk. Okay, this is like the action and reaction principle. Okay, so from this perspective, JL times omega L dot is equal to minus dl times omega L, because it's resisting the motion. Okay, so here we use the minus, but now it is the torque of the stiffness, kappa times theta r minus theta L. If theta r is larger than theta L, this torsional stiffness should apply a torque in this direction, which is exactly opposite of this direction, but their magnitudes should be same. Okay, so let's use our state definitions. Okay, so JL times x1, that's great, minus dl x1 plus kappa times x3. So if I simplify it further, x1 dot is equal to, okay, so let's check that. Okay, minus dl divided by jl x1 plus kappa or k divided by jl times x3. So I computed my second state update equation. Okay, so we are done with all of the equations of motion that we can write on the system, but we want another state update equation which is associated with x3. Okay, so let's do that now. Okay, so let's clean everything. So what is x3? Let's change the color again. Okay, I know that x3 is equal to theta r minus theta l. I need x3 dot, right, which is equal to derivative of both variables, but these are not my state variables, I know that, but let's take the derivative. Okay, derivative of this is equal to omega r. Oh, that's great. This is omega l, but omega r and omega l are my states of the system. So I have that x3 dot is equal to omega r is the first state. So let's check. Okay, no, omega r is my second state. Sorry for that. Okay, so let's clean that. Okay, so it's my second state. You should be careful with the bookkeeping a little bit. x1. Okay, my third and last state update equation. Okay, so we are done with the state update equation. The only thing is we need to put this in matrix form. Okay, so x dot is equal to, so x1 depends on itself. Okay, x1 dot minus dl divided by jl. It doesn't depend on the second state, so it is equal to 0. It depends on the third state, kappa divided by jl. Okay, that's great. So let's move on to the second state equation. It doesn't depend on x1. It depends on x2. So minus dr divided by jr. Okay. So, and here we have minus kappa times jr. Okay. But x2 also depends on input. And we know that x1 doesn't depend on input. So we can write that 0. And this should be equal to 1 divided by jr. So it should be x here, and we should have u here. And finally, x3 dot is equal to 1 minus 1, 0, and 0. Okay, so in state space representation, this is my A matrix, and this is my B matrix. So what is the output equation? Which is very simple, because I know that output is equal to omega L, and omega L is my first state. Okay, so we have a very trivial output equation such that y is equal to first state, so which is equal to 1, 0, 0, x. It doesn't depend on u, so it's equal to 0 times u. This is my output equation. So this is C, this is D. So we are technically finalized the state space modeling of the system. Okay, so in general, if you want to find transfer function, there is no ambiguity about the order of the system, which state you want to use or you don't want to use, because when you do the elimination, everything will be correct at the end if you are, of course, making your computations all right. Okay, but in the state space, state definition can be important. Okay, as you can see, it's not trivial. Sometimes you may overestimate number of states, or you can sometimes underestimate number of states. You should be a little bit careful, and you should solve more problems in this topic. So what I will do is I will change my output. Okay, and while I'm changing the output, I will try to use my previous state equation, but I will only try to change it a little bit. Okay, so if I change my output from omega L to theta L, okay, theta L is the angular displacement of the second disk. So first what I do is I look at the my state variables, I try to understand if I can find theta L as a linear combination of these two. No, I cannot do that. So theta L is here, but it depends on theta R. Okay, so it is not a variable that I can update from this. So what I should do is I should add theta L as a state, which is fine, we can do that. So my state definition is equal to x1, x2, x3, and theta L, okay, which means that x4 is equal to theta L. Okay, that's great, right? There is no problem with this. So I already know the relation between x1, x2, x3, and their intercoupling with also input. So what I need to do is, so this is x4, I need to find x4 dot. x4 dot is equal to theta L dot, which is equal to omega L, and it's equal to x1. So I have a new equation, okay, so let's change the color again, which states that x4 dot is equal to x1, okay, and now my output is equal to x4. So let's change the state space, modify this to fit this function. So what I need to do is first, okay, clean the output equation because it will change, okay. Should I clean this? No, I shouldn't clean that because I can still use that because I know that, okay, no problem. So I will use this part because this part is technically modeling the dynamics between x1, x2, and x3. And I know that x1, x2, and x3 dot doesn't depend x4. So what I do is add 0, 0, 0. So I can clean that because it's not very critical. Okay, that's great. This is now my new x. Plus, I know that the original input only affects the second state, not fourth state. So it is 0, 1 over JR, 0. And now fourth new state equation. Okay, so what I do that, I increase that. x4 dot depends on x1, but only that. 0, 0, 0. And it doesn't depend on input, so it's equal to 0. As you can see, I changed my output, okay, which increased the order of the system because my new output is the integral of another state variable. It can obviously increase the order of the system for some examples, not always, okay. But at least what I did is I used an important portion of the previous solution to finalize my new system because the system is not changing. Only the definition of output changing. Of course, I should use most of the part that I did in the previous part. Okay, so what I can do is now I should do, or let's say, I should technically update my output equation. Now my new output is x4, not x1, because I changed. Now my output is the integral of the first state, so it should be simply equal to 0, 0, 0, 1, x plus 0, u. This is the technical state space representation where u is equal to torque and y is equal to theta L. And if I technically change my output to the omega again, I need to go back to the third order problem, which is technically given in the solutions. Okay, I didn't give this part in the solutions, but it is kind of easy compared to the other parts, and you should be comfortable with changing the states update equations with small modifications.